Welcome to my astrophotography channel called Astrocatastrophe. Hopefully it won't be, but let's see. I want to really go back to basics here. Um, there's a lot of astro channels out there. Um, so I want to try and do something a little bit different, something to capture the audience and all those beginners out there, because yeah, a couple of years ago, I knew nothing. So let's go. So why Astro Cat? Well, on the left you can see one of my best images so far. I mean, it's still not perfect, but it's getting somewhere. That's the Rosette Nebula. And on the right you can see my other Astro Cat, Romeo, Ragdoll. Got two cats. Eloisa is camera shy and she hides everywhere, but Romeo just is perfect for the camera, as is the Rosette Nebula. So let's get into the details. I love this one. The movement of the universe and all the stuff in it. It's constantly moving. I mean, it doesn't stay still like we. We never stay still, even when we're sleeping. What does that have to do with this hobby, this obsession? And that's always a question I get asked. Impact of light pollution. I mean, light pollution takes many forms, and we'll get into that in more detail during the episodes. The different types of objects out there. We all know the planets. We look at the James Webb Telescope images and Hubble and all that, and the galaxies, but there's a lot of images out there, a lot of different images we need to look at. How big are these objects? Now, this is an interesting one. Um, a lot of the images I take are massive in the sky. Unfortunately, we can't see them with the human eye, particularly with my old eyes, but they are big. Okay, so the movement of the universe and all the stuff in it. So, believe it or not, I mean, flat earthers or flurfers, if you're watching this, feel free to comment, criticize, and whatever you do. But it's a fact. We spin at 1,600 kilometers an hour. Yeah, and if we jump and we land in the same spot because atmosphere does the same. Now here we go. It's getting even faster now. The moon travels around the Earth at 3,700 kilometers an hour. Apologies to my English and American viewers. I English, but I live in Austria, so I do work in kilometers. And we're spinning around the sun at a crazy 108,000 kilometers an hour. And that's pretty fast. But let's move on. We, in the Milky Way itself, is spinning at 760,000 kilometers an hour. That's pretty fast. So let's pause for a second. If you think about it, yeah, the Milky Way is massive. So the spin of the Milky Way does not impact our viewing time. The Earth spinning at 1,600 kilometers an hour is what gives us the challenge when it comes to astro imaging. And you can just see it when you look out the window in the morning. And then in the evening, the sun moves. No, the sun doesn't move. We move. The sun is still in the same place. And finally, the Milky Way galaxy itself is traveling through space at just under 2.2 million kilometers an hour. That's pretty fast. That's pretty fast, but during a night's imaging, it's not going to make that much difference. So what does this have to do with astrophotography? I think I've covered these points, but let's go it. We're effectively imaging a moving target where we're moving, not the target. And that's always something to be crystal clear on. So the Earth is spinning, as I said, at 1,600 kilometers an hour. This has the most impact on our image. Of course it does. Have you ever tried photographing a bird or a car or somebody running or anything like that. I mean, it's a moving target. So yeah, we need to consider this, and we'll talk about this in later videos. It's all about the guiding um, and how we guide and how we target and how we focus. Ways to eliminate the impact. Yes, there are many ways to do that, and we'll talk about those in later videos. For example, the Alt-As mount or the go-to mount, and then we'll talk about the guiding scope and how we can really minimize the impact of the fact that we are imaging a moving target. Short exposures. Yes, we can do that. And again, I'll talk more about that in later videos, but short exposures will eliminate the impact of the fact we are moving. But it has its drawbacks when it comes to exposure time and capturing those photons. And that's something we need to consider. All we're doing here is capturing photons. Tracking mounts, do a whole episode on that, and tracking mount with guide camera. So here we go. The very basic. For deep space objects, we are capturing photons. That's light. So when you go into a dark room, you turn the light on. Basically, the room is full with photons. What we're capturing is photons that have been traveling for thousands, if not millions of years. And pause here for a second because I'm hoping the spelling is correct. Yes, they're faint. They need time. So when we look at objects that have a distance of thousands of years, light years, they are faint. Again, one of the many questions I get from friends and colleagues when I show them an image I've taken, it's like, how can you see that? And it's like, I'm exposing my camera for, I don't know, 180 seconds, and there's the image in real time. They need time. If we can keep our eyes open for 180 seconds on focus on one object, you can see it. My daughter, much younger, she can see Andromeda. I can't. I'm old. So here we go. This is a single image of the Pinwheel Galaxy 25 million light years from Earth. It doesn't look anything, but I think you can all agree that you can actually see the faint haze of a galaxy 25 million light years away. Oh, just by the way, my furthest target is 1.2 billion light years. We'll do another episode on that. This was shot, and here's an interesting one. Again, I will do a full video on this. 180-second exposure, or 3 minutes in old money, at 250 millimeter focal length. This is not a big telescope. This is my favorite telescope out of all of them. It's my Red Cat 51. I love cats. I love the Red Cat. So most, if not all, of my images and tutorials that I'll be sharing with you will be focused on the Red Cat. 250 millimeters, although if you look at PixInsight, she comes in at 249 millimeters, but I'm not going to question over 1 millimeter. So short exposures, how long the camera is capturing an image for. Focal length is the optical distance from the point where the light meets the lens of the camera sensor. You can Google this, it's all very technical, but it's basically how long is the eye open for. And it will determine the length of exposure that you can achieve before the Earth's rotation causes star trails. So the shorter the focal length, the longer the exposure. Going back a few slides, Earth moves. The Earth is rotating. And because the Earth is rotating, when you take a long exposure image, the stars will move clearly. I mean, it's obvious. If you look at a headlight of a car when it's driving along, you can actually see the headlight streaming. And we've all seen these images. You can do some really cool images with star trails, but that's not what we're here for today. And there's a rule of thumb. There's a rule of thumb, and we'll talk about this in more detail. So the rule of thumb is 500 divided by the focal length for full frame camera sensors. These are the expensive ones, not the one I have. But so if you got, I don't know, 10 millimeter focal length, then it's 50 seconds before star trailing. Then you get into some more difficult maths for me, at least on a Sunday afternoon. 500 divided by 1.5 times focal length for cropped sensor cameras, the cheaper cameras, the ones I have. But this is without guiding. Always remember, this is without guiding. Once you're guiding, once you're tracking, these rules do not apply. So just an example, which is one of the lenses I've got with my old DSLR, which is 13 years old. 14 millimeter focal length would either get you 35 seconds or 24 seconds. But again, never push it to the max. Never push your lens to the max. You're going to get some weird images and weird stars. So I would always recommend reduce by 30% to be on the safe side. And I've done that to good effect. And here we go. This is the extreme. So I go back to my Redcat 51, unguided, 250 millimeter focal length gives me either 1.4 seconds with a full frame camera sensor or 0.9 seconds. It's not good. This is why guiding is critical. And always, 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 always the stability of the camera. When it's windy, it's not going to happen. When the ground's soft and it starts sinking, it's not going to happen. And I will do some very detailed tutorials on my favorite part of this hobby, the weather. The weather is one of the most critical parts of this passion, hobby, obsession, whatever you call it. But the stability of the camera, that's always a key factor. Anyway, I'm going to pause there. This is my first video of AstroCat. I hope you enjoy it. I won't tell you to do the necessary, which is like press the like button, subscribe, become a Patreon member, blah, blah, blah. I'm just doing this because I love it, and I hope at least one person will learn something and will comment and leave a like, and maybe one day share an image. That's what I'm looking forward to. In the meantime, I need to go and feed my cats. TTFN.